Bismillahirrahmanirrahim. I am Dr. Amir Badshah, lecturer in Department of Chemistry, Cohort, University of Science and Technology. Today, the topic of our lecture is nucleophilic substitution reaction. This is lecture number 11 from the course Organic Chemistry 2nd, having code Chem 3T2. The outline of our lecture will be include introduction, then SN2 and the evidences of SN2 reaction, followed by SN1 reaction and the evidences of SN1 reaction, and then we will discuss which mechanism will be predominates, either SN1 or SN2, and at the end we will mention summary of the whole lecture and will also mention some references from which we have taken this lecture. First of all, we will come to the introduction. As we have discussed in the previous lecture that mechanism wise the reaction divided into three types. One is the reaction which is called polar mechanism, the reaction which involve heterolytic cleavage. Such reaction are called polar mechanism, and this is the example of polar mechanism in which there is a heterolytic cleavage take place, where the bond is cleaved in such a way that the both electrons are taken by one atom. And the other one is the free radical mechanism. The free radical mechanism is that because here the bond is broken down and here both electron is taken by one atom. And in another type is called free radical mechanism. For example, this is a bond when it is broken down, so not both these electrons are taken by one atom, but one of electron is taken by one atom and the other electron is taken by the other. This is called free radical mechanism, which involves heterolytic cleavage. And there is another type of reactions too, in which there is no heterolytic cleavage take place and no homolytic type of cleavage, but involve a cyclic transition state. Then such type of reaction are called pericyclic reactions. But here we will focus only on the reaction where the heterolytic cleavage take place. In this reaction, here this species, this alkyl halide, it is a substrate at which a nucleophile can attack. Here this group along with electron leave, so this is called a leaving group, and the OH group which has electron, which is electron efficient, which is has a negative charge, can attack on this carbon. So a species which attack on a carbon deficient center, it is called nucleophile. It is electron efficient, and the group which is leave along with the electron, that one is called leaving group, and the product which is formed is a result of attacking of nucleophile and leaving of a leaving group is called substituted product. So it is nucleophilic substitution reaction. Here if you see this nucleophile come, this group come is a nucleophile, in this group leave is a nucleophile because it is also electron efficient and this is also electron efficient. So this electron efficient species is displaced by another electron efficient species. It means one nucleophile is replaced by another nucleophile, so it is called nucleophilic substitution reaction. Sometime instead of this reagent, a solvent may be act as a nucleophile too. If a solvent which is used to carry out this reaction picked is a nucleophile are involved in the chemical reaction, then the reaction is called solvolysis. Solvolysis is also a type of nucleophilic substitution reaction. If the solvent we have used is water, then such type of solvolysis is called hydrolysis. And if alcohol is used as a solvent, then such type of solvolysis is called alcoholysis. And if ammonia is used as a solvent, then such type of reaction is called immunolysis. How this reaction takes place? What is the stepwise mechanism of this reaction? So there are two possible pathways for this reaction to be carried out. One is the concerted, which take place in a single step, and the other one is the stepwise. It means this attacking of nucleophile and the leaving of living group side, if it takes simultaneously, then it is called concerted mechanism. And if a living group leave first, and then in the following step nucleophile attack on this carbon deficient part, then it involves two or more than two steps. And such type of reaction or mechanism will be the stepwise mechanism. So a reaction, if the reaction proceed through concerted way, then such type of reaction is called SN2 mechanism. It means it takes place in the one step. This SN2 mechanism was introduced by Sir Christopher Ingold and Edward D. Hobbs in 1930, where in this mechanism the attacking of this nucleophile and the leaving group and the leaving of this living group take place simultaneously. It means it take place in one step where the leaving group leave and the attacking group attack or nucleophile attack take place in one step or take place simultaneously. If it takes place in one step, then it will follow the SN2 mechanism. Is shown here. Here nucleophile attack on the electrophilic center, it means the carbon, and the leaving group, the leaving of living group take place simultaneously, and we get the substituted product as well as the living group. If it follows this mechanism, then it is called SN2 mechanism. Now, what are the evidences? How we will know that the reaction has followed the SN2 mechanism? So there are some evidences. From those evidences, we can easily find that has the reaction take place through SN2 or through other mechanism. First evidences is the kinetic studies. From the kinetic studies, we can find the rate, that what are the factor in we can find the rate, and there are various factors which is affecting the rate. One factor is the concentration. If both the concentration of the substrate as well as nucleophile affect the rate of the mechanism, then it will follow second order mechanism. It means the rate depends not only on the molar concentration of the substrate, but also effect on the molar concentration of the nucleophile. Here the rate is directly proportional to the molar concentration of the substrate in nucleophile, and then it is further simplified as rate is equal to k, where k is the rate constant multiplied by the molar concentration of the substrate and molar concentration of the nucleophile. And that's why this reaction is called SN2 mechanism. It's where S represent substitution reaction and N represent nucleophile, and this two represent bimolecular. It means its molecularity is 2. What is molecularity? It is defined as the number of molecule which involve in the rate determination step. So here the two molecules, it means the substrate in nucleophile, both are involved in the rate determination step, so it is called bimolecular. So that's why we have written is 2 has been written here, and it involve the substitution of one nucleophile by another, so n has been written here, and it involves substitution, so s has been written here, so we can write s into. You should remember that in should be written a little bit down. S and 2 will be in the one line. If we have mentioned in the previous slide that sometimes instead of nucleophile, solvent can also act as a nucleophile. Sometimes nucleophile, a special reagent is used as a nucleophile, but sometimes instead of reagent, a solvent can act also as a nucleophile. If a nucleophile involved in a reaction, in a nucleophilic substitution reaction, then order of such reaction will be not second order or bimolecular, but it will be a pseudo first order reaction. Pseudo first order reaction is that in which only one substance can affect the rate of the chemical reaction, although other substance, second substance is present, but its concentration is so much high that there is no visible detection that whether it affect or not. Then although it involved in the reaction, but its concentration is so much high that we cannot find its effect on the rate of the chemical reaction, then such type of reaction in such type of reaction will be of pseudo first order reaction. The second evidence of SN2 reaction is the stereochemical studies. In stereochemical studies, we know that there are some configuration which are or in some configuration which are S. So in the SN2 mechanism, here a take place from the back side, and if it means it doesn't attack from the side through which a living group live, but it attack from the back side. Here you can see this group, this living group live from that side. This is the front side is shown here. This is represent the front side and this represent the back side. The front side is due to the group which is live. So the group live from this side, so this is the front side and this is the back side. So here attack take place from the back side, not from the front side. Why not from the front side? Because this living group has blocked this face. So when the nucleophile attacks, so nucleophile will attack from the back side compared to the side where the living group can live. So if attack plays from the back side, attack inversion of configuration will be take place. It means the configuration will change. Here you can see that the configuration of this substrate is S. The priority of this is 1 and the priority of this is second. And if we move from this to this, here we will have to change the position of hydrogen with the methyl group. So if we change, if the methyl come here, so its priority will be 3, and if we will move here from this side, so it will appear as right, but actually we have changed one position, so it will be the S1. So here attack from the back side. Due to the back side, we will get this substituted product, and the configuration of this substituted product will be the S. If we will have to change again the position here, if we change again the position, the first priority will be of OH group and the second priority will be of the ethyl group and third priority about the methyl. So it will be go in this direction. It seems S, but in actually we have changed the position of hydrogen in methyl, so it will be the R1. So It's mean here, if the configuration, if we have a optical center here, or stereo center here, or asymmetric center here, and if the configuration change is a result of this reaction, so it's mean that here SN2 reaction has been take place. Mechanistically it has been shown here, when it attack on this species, so we get a transition state. In a transition state, the bond between the carbon center and nucleophile involve the formation, and as well as it's simultaneously the breakage of the leaving group and the carbon center take place, and this species is in a transition state, so in a transition form, so that is why it is called a transition state. And after the transition state, this group leave and the OH can attack from the back side, and we get this substituted product. But compared to the substrates, its configuration is not the same, its configuration is changed, so that's why this due to it will follow the SN2 mechanism. Now the mechanism of the reaction may be SN1 2. As we have discussed, the mechanism may be SN2, and then there were evidences for that. The second one is the SN1 mechanism. It means that the reaction may be take place through stepwise mechanism. A stepwise mechanism is that one which is not involve a single step, but involve two or more than two steps. What are those steps? In the first step, the loss of the leaving group to form a carbocation, and in the second step, a nucleophile can attack to form the substituted product, is shown here. Here the leaving group leave to form a carbocation, and in the following step, the nucleophile attack on this carbon to form the substituted product. What are the evidences through which we can guess that this reaction has been taken place through SN1 mechanism? Number first evidences is the kinetic study. Here the rate only depend on the concentration of the substrate and not depend on the concentration of the nucleophile. So if only the concentration of the substrate affect the rate, so we can easily guess that this reaction has been occurred through SN1 mechanism, and that's why it is called SN1, where this one represent unimolecular. It's mean one molecule which is substrate involved in the rate determination step, and this represent nucleophile, where nucleophilic substitution, it's mean one nucleophile has been replaced by another. And what happened here, substitution take place, it's mean one nucleophile substituted by another, so that's why it is called SN1 mechanism. In SN1 mechanism, the slow step is the first step, the second step is the fast one, is shown here by this apparatus. That as the reactant change into the product, the first step that we have discussed in the previous slide, that the first step is the slow step and the second step is the fast step. So in the first step, diagrammatically it has been shown here that one is the slow, because this is the narrow part. So when the scent come from this compartment into this coming of the scent from this compartment into the bottom compartment depend only on this opening, not depend upon on this opening. Why it is so? Because it is the narrow one, it is the slow one, and it is the large one, it is the first step. So in the formation of the product in SN1 mechanism only depend upon on the rate determination step, not depend upon on the second step. because the rate determination step is the slow step and the following step is the fast one. Now, what are the evidences through which we can say that this reaction has followed the SN1 mechanism? Number first evidences is the stereochemical study. What happened here? A racemization takes place. Remember, racemization is the phenomenon in which half part of the molecule retain the configuration in half molecule. Half molecule retain the configuration in half molecule. Inversion of configuration take place, so we can get a mixture of both S and R. If we get a mixture of both S and R, then such reaction is a racemization reaction. From stereochemical point of view, we can say that a racemization has been occurred, is shown here. Here, this is the molecule having R configuration. When OH attack on this one, so we can get two products. One is R and one in S. So one half of the molecule has the same configuration as like that of the reactant, and half of the molecule has changed their configuration. They have been changed from R to S. How it happened? When OH attack, when in the first step we get a carbocation, then in the following step OH will attack. So there are two possibilities of the OH. The OH can be attacked from front side. It means the OH can attack from the side through which a living group live, which is that side, and the other one which can attack from the back side. If it attack from the same side through which the living group has been lived, then we will get a substituted product which has the same configuration as that of the reactant. If it has attacked from the back side, then we will get a substituted product whose configuration is different from that of the reactant. So a reaction in which both R and S are formed in the same amount, then such type of reaction is called a racemization reaction from stereochemical point of view. But one thing should be remembered, that inversion, it means the concentration of the inverted product is a little bit more than 50%, and the configuration of the inverted product is more, and the configuration of the retained the configuration of the product where retention take place, here retention take place is a little bit less than 50%. Now the question arises here, why it is so? Is it has been shown here through model that when living group live, so here a carbocation is obtained. This carbocation can be attacked from front side as well as from the back side, but in the front side you can see when it attacks from the front side, so in that case the configuration will be remain the same. If it attack from the back side, then the configuration of the product will be changed. But if the retention take place in the retention product, the product where there is configuration has been retained, the percentage a little bit less than 50%. Why it is what is the reason? This is due to ion pairs which are present here. Here this living group is also here in the proximity, and the positive charge is the positive ions are also present. So this living group can produce a hurdle in attack when a nucleophile attack from the side, so that's why its concentration is a little bit less. Why it is so? Because when the leaving group leaves, so the concentration of the leaving group is more here, so that's why it produces hurdle in the attack of nucleophile. So that's why the here the product which is obtained from the front side will be a little bit less. It means here the product obtained where the configuration will remain the same as that of the reactant, so its concentration will be less. So that's why the configuration of sorry so that's why the configuration of the product where the retention involved will be less than 50%, and the product where inversion takes place whose concentration will be a little bit more than 50%. Now we are coming to the evidences of the third evidences of SN1. If we get a rearranged product, that means the reaction has been occurred through SN1, not through SN2. For example, if we consider this reaction, this leaving group leave and form this carbocation. This carbocation is a primary carbocation, and we know that a primary carbocation is less stable than secondary, and secondary carbocation is less stable than tertiary carbocation. So in that case, this methyl group leave along with electron and will attack at this position, and we can get this carbocation which is a tertiary carbocation. And why it happened here? Sorry. This is because this was the primary carbocation and this is the tertiary carbocation, and tertiary carbocation is more stable than the primary, so that's why this methyl group shift along with the electron and attack on this carbon, and as a result this carbocation is obtained. Then nucleophile attack on this species and we can get this product. But this here the leaving group has been left from this carbon, but nucleophile attack on this carbon. It's mean the leaving group, the position at which attack of the nucleophile and the position from which leaving group has been left not the same, but it is different. The leaving group has left this carbon and the nucleophile has attacked on this carbon. It means we have get the rearranged product. If we have got a rearranged product as a result of a nucleophilic substitution reaction, then we can easily guess that the reaction has been taken place through SN1 mechanism and not SN2 mechanism. Now, what are the factors which decide that whether the reaction has been take place through SN1 or SN2? If we want that a reaction should follow the SN1 mechanism, so what are the factors should be that favor the SN1 mechanism, or what are the factors which favor the SN2 mechanism? So these are the four factors which can decide that the reaction will take place through SN1 or SN2 mechanism. Number first one is the substrate. We know that substrate in SN1 mechanism, the substrate form carbocation. In carbocation, the tertiary carbocation is more stable than secondary, and then secondary is more stable than the primary, and primary is more stable in the methyl carbocation. So a reaction, if a substrate can form tertiary carbocation, then it will favor SN1 mechanism compared to the SN2. It means if as a result of a chemical reaction we can get primary carbocation, then it will not favor SN1, but if it form secondary carbocation, then it will favor SN1. The rate of SN1 will be enhanced, and if it form tertiary, then the rate of SN1 mechanism will be further enhanced. It means if we go from the primary to secondary and from secondary to tertiary, so the rate of SN1 mechanism will be enhances. So it means the tertiary carbocation will favor a substrate which can form a tertiary carbocation will favor SN1 mechanism more. So, in case of SN2 mechanism, we know that from the mechanism that attack place from the backside. So in the backside attack, it is easy for a nucleophile to attack the primary carbocation or methyl radical compared to the tertiary carbocation and secondary carbocation due to hindrance. In case of substrate which result tertiary carbocation, here it show hindrance for the nucleophile to be attacked. But in case of methyl carbocation, primary carbocation, there is no hindrance for the nucleophile to attack. So in case of substrate which result tertiary carbocation will favor SN1, and in case of substrate which result methyl carbocation, primary carbocation will favor SN2 is shown here. If in a reaction which result primary carbocation, the rate of SN2 will be more. If it is secondary result secondary, then the rate will be decreases, and further if it result tertiary carbocation, the rate of SN2 will be decreased further. The second dissociative factor is the nucleophile. Nucleophile, there are three types of nucleophile. One is the strong nucleophile, second one is the moderate nucleophile, and the third one is the weak nucleophile. In strong nucleophile, how we will know that this nucleophile is strong? If a nucleophile has a negative charge and the negative charge is not stabilized, then such nucleophile are considered a strong nucleophile. For example, in case of alkoxy ions and amide ion, here this negative charge only concentrated on oxygen, here the negative charge only concentrated on nitrogen. So these are strong nucleophile. If it has negative charge and the negative charge is stabilized, then such nucleophile are considered moderate nucleophile. For example, in case of halogen, the negative charge is stabilized because the halogen has high electronegativity. In case of tosylate, we will discuss the structure of tosylate and carboxylate later on. Here the negative charge are stabilized through resonance. So such it has negative charge can act as a nucleophile, but they are moderate because here the negative charge is stabilized. One is the weak nucleophile, which has electron but has no negative charge. Electron are present in the form of lone pair of electron. This species can also act as a nucleophile, but that will be the weak one. For example, in water, here oxygen has lone pair of electron, here oxygen has lone pair of electron too, and here nitrogen has lone pair of electron too, and here in the neem nitrogen has lone pair of electron. They can act as a nucleophile, but they can they are weak nucleophile. So which type of nucleophile will favor SN1 and which type of nucleophile will favor SN2? In case of SN1 mechanism, we know from the mechanism that nucleophile is not involved in the rate determination step, so the nature of the nucleophile has no any effect on the rate of SN1. If it is weak, or if it is moderate, or if it is a strong nucleophile, the rate of SN1 reaction mechanism will be remain the same. It will have no any effect. In case of SN2, a strong nucleophile will favor mostly SN2 mechanism, as it has been shown here that as if a nucleophile is weak, then the rate of SN2 mechanism will be slow, but if it change from weak to moderate and from moderate to strong, the rate of SN2 reaction will be increases. Third one is the effect of leaving group. Leaving group mainly are three types. One is the excellent leaving group, second one is the good leaving group, and the third one is the bad leaving group. Excellent leaving group are those which has no negative charge, only has the negative the electron present in the form of lone pair, for example H2O, alcohol, ammonia, and primary amine. The good one is that one which has negative charge but it is stabilized, for example halide ion to silate in carboxylate. And the bad one is that one in which has negative charge but it is not stabilized, for example here the alkoxy ion has negative charge but it is not stabilized, and here nitrogen in amide negative charge is present but it has been not stabilized, so it is a bad leaving group. So SN1 mechanism can affect by the nature of the leaving group. If a leaving group is excellent, then SN1 will be favored. SN1 mechanism, if the leaving group is bad, so it will never follow the SN1 mechanism, but if it is good, still it follow SN1 mechanism. It has been shown here is that the rate of SN1 depends upon on the nature of the leaving group. If it is excellent, then the rate will be very high, but if it good, still SN1 mechanism will occur. And if it is bad, so the rate of SN1 mechanism is very low. It's mean not possible with a bad leaving group. For SN2 the leaving group, the nature of the leaving group can also affect, but for the leaving group at least it should be good. A leaving group excellent is far better, but a good leaving group can also if a group is good leaving group, then it will also follow SN2 mechanism. If the group is excellent, so the rate of SN2 mechanism will be high, and if it is good, still it is high, but if it is bad, this rate will be slow, but it comparatively higher compared to the SN1. So both leaving group, if the leaving group can affect both, the nature of the leaving group can affect both SN1 and SN2 mechanism. Excellent leaving group can favor both SN1 as well as SN2 mechanism. Number third one is the solvent. Fourth one is the solvent. Solvent is mainly of for the nucleophilic substitution reaction, the solvent should be polar in nature. But the polar solvent is mainly of two types. One is the protic solvent. A protic solvent is that in which hydrogen is directly bonded to a more electronegative atom. For example, water, here hydrogen is bonded with oxygen. Similarly, in alcohol, hydrogen is bonded with a more electronegative atom, oxygen. Similarly, in ammonia, hydrogen is bonded with a more electronegative nitrogen. Second one is the aprotic solvent. It is polar, but they are aprotic. What is mean by aprotic? Where there is hydrogen is not directly bonded to a more electronegative atom. For example, in case of DMSO, the structure of DMSO is this one. So in this case, there is no CH3 here and CH3 here too. So here is no directly bonded oxygen hydrogen to a more electronegative atom. So such type of solvent is called aprotic solvent. For example, DMSO, DMF, and acetonitrile. In case of SN2 mechanism, aprotic solvents are needed. It has been shown here that in case of here that bromine is can leave and it's substituted by this in 3 negative group azide group. So a nucleophilic substitution reaction takes place. Now how this reaction has been affected by the nature of the solvent. If the reaction takes place in the methanol, the rate will be very slow comparatively. If we change the nature of the solvent from the protic to aprotic, this side we go from the protic to then for methanol change to H2O, the rate is a little bit high, and then DMS, so the rate is going very high, and then DMF, and then methyl. So if we go from left to right, it means from the protic solvent to aprotic solvent, the relative rate of this reaction will be enhances. So since this reaction takes place to SN2, and if the nature of the solvent change from the protic to aprotic, the rate of the reaction will be increases. Now why it is so? The reason is that because the polar aprotic solvent rise the energy of the nucleophile. Here, for example, a nucleophile has been formed here. This nucleophile is not interact with the aprotic solvent. It does not interact. If there is no interaction, then the activation energy of this nucleophile will be higher. So if we use polar protic solvent, the activation energy of this nucleophile will be higher. But if we use polar aprotic solvent, then the energy of activation will be low. So it enhances activation energy of this. So if the activation energy here now it is less compared to the polar protic solvent, if it is less, so then the reaction rate will be high because less energy will be needed to pass from this transition state. But if we use protic solvent, then it will favor SN1 mechanism. Why it is so? Because here if we use polar aprotic solvent, in the polar aprotic solvent the chloride ion is not stabilized, but if we use polar protic solvent, the chloride ion is stabilized here. So if it is stabilized, then it will be easily pass. Here the activation energy is less compared to that. But if we use polar solvent, the polar aprotic solvent, then the activation energy is so much high. Why it is so? Because in the polar solvent it stabilizes the carbocation which is formed as a result of a chemical reaction, and it also stabilizes the nucleophile. But when it is the carbocation is formed here, so the carbocation here is stabilized more by the polar protic solvent compared to the polar aprotic solvent. So when we use protic solvent, then it will favor SN1 mechanism. The nature of the polarity can also affect the order of reactivity too, and that phenomenon is called nucleophilicity, that we will discuss in detail in the coming lecture. If we use protic solvent, then these species can act as a nucleophile in the SN nucleophilic substitution reaction. If we use protic solvent, then the nucleophilic nature of these species is in such a way that iodide ion is more nucleophilic than bromide, and bromide is more nucleophilic than chloride, and chloride is more nucleophilic than all. But if we use aprotic solvent, then the reverse of nucleophilicity takes place. Here the chloride ion is more nucleophilic than chloride, and chloride is more than bromide, and so on. What's the reason here? Because here if we use protic solvent, so it will interact with chloride ion more compared to chloride ion. So if there is more interaction, so it will not free to be attacked. But if we use aprotic solvent, here the nucleophile cannot interact with the aprotic solvent, so they are free to be attacked. So that's why the chloride ion will be more nucleophilic compared to the other halide species. In summary form, we can say that what are the factors which favor SN2 and what are the factors which favor SN1. If the substrate is methyl or rambry, then it will favor SN2. But if the substrate is tertiary, then it will favor SN1. Similarly, if a nucleophile is a strong nucleophile, then it will favor SN2. But nucleophile, the nature of nucleophile has no effect in case of SN1. So if a nucleophile is weak, it will favor SN1. Similarly, the nature of the leaving group can affect both SN1 and SN2. Excellent as well as good leaving group are necessary for SN2, but for SN1, a leaving group should be excellent leaving group. Similarly, solvent can also affect SN2 and SN1. If a solvent is polar aprotic, then it will favor SN2, and if it is polar protic, then it will favor SN1 mechanism. These are the references if you want to study it more, and thank you for watching this video.